in a RAG or a context-based question answering setting. So let's get started. Okay. So as we all know that the large language model has shown remarkable capabilities in instruction following, and retrieval-augmented generation is one of common method to provide external knowledge, for example, like context or domain knowledge for large language model to answer the question. So, however, there are significant limitation remains in this common technique. For example, like when the context length is too much, or it contains noise or irrelevant fact, then the large language model may fail to leverage and extract the relevant evidence to correctly answer the given questions. For example, here in the right side, we have an example where in a context-based QA, uh, the large language model is given a context about a special force, an army organization, and the model is asked about a specific events within the context. And here, when using a vanilla decoding, the model wrongly uh, the wrong answer is about 1945, and this phenomenon can lead to factual hallucination and factual inaccuracies in the LLM question answering and text generation. So here in this paper, the author has proposed a novel method to automatically identify relevant evidence within the context, and use that to support the large language model so that they can generate a correct answer. Uh, so let's talk more about the technique. The first important thing is self-guided evidence eliciting. So here in this paper, the author they leverage the model's internal representation, specifically the attention distribution when a model perform the forwarding step. So uh, their hypothesis is that uh, the self large language model they already know which facts or which sentence is important in the context, so they will assign a more higher attention score to that sentence. So here they compute a sentence level attention from the average of token level attention from the given input. Here we have the vector A. So one of their first analysis is they point out that the deeper layers they can pay greater attention to the evidence in the context, even though the answer is correct or not. So here in the chart, we can see that for three different LLM backbone, Llama 3.1, Mistral 7 billion, and Nguyen 2.5 7 billion. Um, when the layer index is deeper, for example, like from the layer 16 to the last layer 32, the attention score that assigned to the evidence sentence here is much more higher than the non-evidence sentence, which is in the red line, the green line compared to the red line. So uh, from this result, you can see that the LM itself can pay attention to the correctly and the relevant evidence within the context, and so that we can leverage this attention score to identify correctly and relevant evidence within the long given context. So that's how we can identify them. And from that observation, the author they propose the sentence evidence score, EI, which is computed by the attention score from a subset of layer from the large language model for example, 7 billion LM, they had 32 layers, and in this method they use 50% last layer of the LM model to compute the attention score, and then they set a threshold alpha, so that if the sentence score is greater than alpha, then it is assigned or predicted as the evidence sentence and will be used in the later. So this is a fixed threshold in this method. And next, after we have identifying the evidence, here in this method they use a highlighting method to guide the model to pay more attention into the evidence explicitly. So here they use a prompting method that use special token start important and important before and after each evidence sentence that they had identified in the previous step, and then they update the task instruction to guide the model pay more attention toward the highlighted sentence. Here I have the prompt template for illustration. So this is a quite simple but effective method to guide the large language model toward the highlighting sentence. So overall, the self-elicit procedure can be summarized in the algorithm one, where we have a large language model and input context and question. So the first step is we will generate only one token with this setting to get the attention distribution from the from the LER, which is a layer that we want to compute. For example, like the last 50%, and then we will get the evidence score E using the equation 3, and select the evidence sentence using equation 4 with a fixed alpha threshold. And then the new context is obtained by using the highlighting methods with the start important and important token. And finally, they generate the new answer with this new context to get the final answer, which would be more accurate and more factual accuracy. So for the details about the experiment setup, here they use exact match and token level F1 for measuring the quality of the answer. And then for the benchmark, they use four different, which is hotspot QA, news QA, TQA, and NQ. I have the table for dataset statistics and sort in the slide. So one of the notes is that this dataset is from the general domain, and it's mainly from the question answering task. For example, like the answer will contain only one or two words, and it will ask about time or about people or about organization. So it is a quite simple answer type, not like the long or free text generation. And for the hyperparameters of the self-elicit, as I have mentioned, they use the last 50% layers from the LM to compute the attention score, and then a fixed alpha threshold is set at 0.5 to identify which sentence is it should be highlighted as the evidence. And for baseline for comparison, they compare the self-elicit with the chain of thought prompting, a very common and well-known prompting method for LM. And then they compare the self-elicit to full elicit, which highlight all of the given context as the evidence. And another kind of is prompt elicit, which use a prompting method here as I have on the slide to identify the supporting evidence and then answer the question in the one step. So that is three different baselines for comparison. For the main result, as we have here, we can see that the first insight is full analysis does not provide meaningful improvements as we expected when we mark on the given context as the evidence, then it will include on the noise and irrelevant facts. so that the large language model might fail to correctly answer the question. And then one of the well common reasoning enhanced methods is chain of thought. They show an inconsistency improvements among LM backbone, which means that this method does not directly address the problems of hallucination and factual inaccuracies in these QA setups. And then finally, the proper method SelfElicit, they significantly and consistently improve the QA performance across 4 benchmark and 3 different LLM backbones, so that we can see the effectiveness of this genetic-free method. And here we have some more analysis about how the SelfElicit highlight relevant evidence. So in the left side, we have the illustration of 4 different examples when the proper method correctly highlight the relevant evidence and leading to a correct answer when we compare to a base vanilla decoding method. And on the right side, we have a sentence level evidence identification when the author they use a fact score or sorry, they use a fact sentence that already provided within the dataset, and they use it to measure the evidence identification quality of the SelfElicit and measure by RO ROX and NDCZ. And we can see that across 4 datasets, the accuracy of SelfElicit in identifying evidence are quite impressive. And so that which means that the method can effectively identify evidence within the given context. And here, when we want to assess the effectiveness of the SelfElicit in a more noisy context, for example, like we add more irrelevant facts into the context, which can give more noise or more length into the context. We see here that the SelfElicit they still successfully to improve the performance compared to the base, even though in the noisy context. And one of the interesting points is that with noisier context, the methods they highlighted less sentences, so that in this adaptive way, the SelfElicit method they can reduce the number of highlighted sentence, and so that they can reduce the number of noise and irrelevant facts to the model. So that explains how the SelfElicit method they can still improve the performance even though in the noisy context. And then we validate the choice of the LER, which is the layer we use to compute the attention score. So this is a hyperparameter choice. So when they compare it with the different choice, like for example, like here, using on the layer or using the first half and the second half. So we can see that choosing the last 50% of the layers achieve the best metric in both the elicitation accuracy, which means that it can identify correctly evidence, and also it achieved the best QA performance, which means that we generate a correct answer. So here they set this last 50% of layer as the default setting for the LER. And for the choice of the alpha, they they perform a research and a more experiments to see the effectiveness of the alpha into the QA performance across 4 benchmarks. So here we can see that for dataset with simple reasoning requirements like the NQ, the best performance is achieved at alpha equal 1, which means that very little number of sentences are highlighted as the evidence. So, but however, when they are multi-hop reasoning, which means that there are multiple evidence required to solve the question. The optimal alpha is achieved around 0.5. So from these observations, they set the default setting for the alpha is at 0.5, and it is a fixed hyperparameter in their method. And finally, we have a analysis to compare between the highlighting and the filtering method when we apply our identified evidence. So here we have a baseline is FUCO. So in this FUCO method, they employ a fine-tuned lemma 2 to identify the evidence in the context instead of using the old target large language model. And for the filter, they extract the unidentified sentence and you and concatenated them into a new context, which is very similar to unlike extractive summary. And for the highlighting method, it is the original method of the self-elicit. And from the table 11, we can see that self-elicit highlighting, they consistently outperform the filtering and the FUCO methods. So this so this is the reason why they employ the highlighting method here in the self-elicit. And also the problem of the filter method is that it's behave as a extractive summary, so it might struggle to process, and they might lose the coherence of the uh, context when we facing with like the QA context when we dealing with like news or a newspaper. So in this filter, they might serve as an executive summary, and that's why their performance on this QA setting is not good compared to the highlighting. For finally, this self-elicit method, they leverage the internal attention for automatically contextual evidence highlighting, and they improve both the QA performance factual effectiveness of the large language model in inference and training-free method. For future work, we can dive deeper to study a way to set a adaptive threshold alpha based on the model or the data characteristic. And we can also extending this method into more diverse tasks, for example, like text generation. So that's all for my presentation. Thank you for your listening. And if you had any questions, please feel free to ask me.
Thank you, Minh. And yes, so any questions from Lemmer, please?
Hello, Minh-san. Can you hear
I
me?
have some. Yes.
Yeah. So thank you for your very detailed presentation. I have a question in the slide 13, I think.
Okay,
It's about the highlight ribbon. Yeah, this one. So I missed your presentation about this slide. So can you explain me about the metric, the sentence levels outlook and the sentence level NDCG?
Okay. So this for the first thing to note here that the experiment here is to assess the quality of evidence identification instead of QA performance. So the authors, they use the fact sentence, the metadata fact sentence in the benchmark to as a goal label for the highlighted sentence. So here in the RC and NDCC, they measure the quality of the predicted evidence. So and higher, which means better. So here we can see from the result that the performance of self-elicit in evidence identification is pretty good and impressive across all benchmarks.
So you mean like from the original evidence, like the author, they already have the golden highlight sentence for each evidence.
Yes, they had the golden fact sentence in the method in the dataset,
I see.
and
And
yeah, they compare the predicted sentence with the gold sentence to assess the quality of identification.
yeah, because I think this is the main how to say, maybe this is the highlight objective that this paper talking at the introduction, I think. But I also curious why they don't like compare this metric with other methods, for example, like full elic or like prom elic, full elicit and prom elicit.
Yes.
Yeah.
So for the full analysis, they consider all the context as the evidence. So I don't think the full analysis should be compared here. And for the primary analysis, I think that it could be considered here, but I think that they already compare them in the QA performance. So here they only want to focus on the identification ability of the cell analysis. So that's why they don't have these two baseline here.
Yeah. Okay. So that's all my question. Thank you for your answer and the presentation.
Okay, thank you for your question.
Yes, thank you, Hyun. So, any the other questions or comments, please?
Hello, Misa.
Me.
Thank you for your presentation. And
Hello, Technician. Can you hear me?
Hi, Sam.
yes, so
Yeah. So thank you very much for your presentation. So I have two questions about. Can you back to slide number 4?
Okay. Yeah.
Yeah. So why do deeper layer attention score better to capture relevant evidence to compare to the shallow layer?
Okay. Thank you for your question. So actually, they do not have a valid and explanation for this phenomenon. They they solely use this pattern to apply into their method. But however, uh, in some in some other papers I have read, they have proposed a metric called information flow, and they have measure the information flow within the layers of the large language model, and they also saw a similar pattern where the most intermediate and the last layer they pay more attention to the relevant facts, and instead of the instead of the first layer. So in my opinion, maybe the intermediate and the final layers they have compute enough interaction and distribution along the context and along the layer, so that they can they can have a better mapping between the question and relevant evidence. So that's why intermediates and the last layer they have ability to correctly identify relevant facts in the context.
Oh, yeah. I see. I got it. So thank you. So can you back to slide 19?
Okay.
Oh, okay. So how do you think about self-implicit be extend to closed book QA scenario or a proprietary model without attention score?
Oh, for the closed book QA, you mean that the question answering without external context?
Yeah, yes.
Oh, so I think the extension of self-elicit to closed book QA is not feasible since we leverage the attention on the question, but however uh, we can somehow identify key information within the question instead of context in the closed QA, so that for example, like we can guide for very long or complex question, we can guide the large language model to key information in the question. And for an alternative to attention score, I think we can leverage the maybe the entropy or the probability distribution uh, in the large language model instead of attention. So, for example, like we can treat the entropy of a predicted token as the confidence score of the model. So we can combine it with the original distribution or with some method or some weight. So yeah, that will be the future work.
Yeah, I got it. I know you understand. So thank you very much for your answer. I will discuss you later. Thank you.
Oh, thank you, Chung Sang, for your question.
You too, sir. Yes, maybe I have one follow-up question with the Chung Sang about the fingers, the finger about the relation between the attention score and layer.
Yes.
In here, we can see that the relative attention score is picked at the middle layers.
Yes.
And they drop at some last layer. And this is similar to in all three model here.
Yes.
And can you explain this the features? Why they pick up the intermediate layers and drop significantly in the last layer?
So actually, I haven't researched deeply into the reason behind this phenomenon, but however, I can suggest a paper that they also point out a similar results in this behavior of the large language model, which they call exploiting contextual knowledge in LM to reusable information-based layer enhancement. So for simply they in the other paper they measure the entropy as the information flow between the layers, and they also conclude a same result that the intermediate layer they focus most on the relevant evidence, and then somehow reduce gradually to the final layer, and then they propose a method to amplify the information from the intermediate layer to the final layers so that they can reduce hallucination. This is another paper. So, but for the theoretical reasons for this pattern, so maybe I cannot answer this immediately, and I will discuss with you later.
Yes, meaning just if we apply the method based on answers, we do not need the second forward pass highlighted context. Is correct. Meaning that because we can input the attention score or the most important evidence from the middle layer to the last layer. So we do not need the second forward pass, where in this paper they use the second forward pass using the highlighted context. Is it correct?
Yes, they actually have to forward 2 times. The first one need to identify the evidence, and the second time need to actually generate the answer.
So therefore, in based on your answer, we do not need the second one.
Yeah, I think that is feasible, but we have to modify the decoding process to directly inject the attention from intermediate layer to train the token probability distribution when predicting the answer. So I think that would be more complex in the technical terms, in the engineering terms.
I see. So maybe it's also a follow-up questions about this, where how these people highlight the important points. They used a token, a special token, a stat important and importance.
Yes.
And what do you think? Instead of using the the hard tokens like the start important and end important, we use more soft methods like we directly modify the attention score instead of prompting the special token. We directly make the model bias on the the importance sentence. So do you think?
Yeah. Thank you. I think that is also an interesting future work that could be feasible when I think we can add like an attention weight or score to tokens that lies in the highlighted evidence when we compute the token probabilities. And but I think one of the main limitation of this direct method is that it will not be integrated to like flat attention or other kind of attention. Since as I know that flat attention they doesn't support looking or modifying the attention score in the in internal processing of the model.
Okay, I see. So okay, and maybe the last question is about this about the context length of the data set the author's experiments. We can see that the normally the context length is under 4,000. And do you think if we like experiment with more long context or like the long context data set around like 100,000, do you think this method can work or not?
I think if the contact length is like 100,000, it may be impossible if we only have like academics resource infrastructure like one or two nodes of 100. I think it might not be enough to compute the attention matrix here. See, from my experiments with 286,000 GPU, a total of like 100 GB of VRAM, I can compute to maximum of like 2.5 token to 2000 and tokens, and I have to make some modification to the socket to be able to achieve some quite longer, but not still enough for some very long context setting. So yeah, I think the scalability of this method they might not be enough for commercial or other settings.
Okay, I see. But if we do not care about the computational resource, we only focus on the theories of the methods, how that they can apply to the long context and should is work in the long context. And what do you think about in this case?
Also,
if we do not care about the computational resource.
Okay. Yeah. In theory, I think that the scalability is it's not a problem with 1000 case tokens in the method they doesn't have any limitation for the contact length uh, as we make sure that the contact length is enough for is in the range of the model contact length, so it will be fine. But yeah, as I said, the requirements for computing resource is will be much significantly.
Okay, I see. Maybe we to verify this claim, maybe we need to experiment because for the long context, maybe we use observe some problem like the lost in the middle where they forgetting about what the previous context say, and maybe we need experiment with the long context to verify this. And yeah, okay, I see.
Yeah, I see the point. Yeah, just will be also an interesting problem if we actually scale this to a very long context. Yeah.
Okay, I see. So thank you for the answers. And yes, I have one more question. And maybe no, Asan, you want to ask something? Because I see your open job microphone.
Yeah, thank you. Actually, I like your presentation, but I have a question about the process of calculating the evidence score. So, can you go back to that slide? How you describe? Yeah, how to
Yes.
describe you calculate the evidence score? Maybe the slide 4.
Okay. So here.
Slide 5. Yeah. So
okay. Yeah.
here I see that is the evidence score is some sort of combination between the score throughout on the evidence reading layer, right? So I wonder how they design this layer or set up this layer in this architecture.
Okay. Thank you for your question. So for these evidence layers, they consider it as a hyperparameters, and as I mentioned here, they have an applied some study to validate the choice of evidence layers in the model. So here they actually experiment on the llama 3.5 x billions, and they can see that the optimal setting for the evidence layer is use the last 50% of the model layers to compute the attention score.
Oh, I see. Okay.
Yeah, so actually this is a model and task specific hyperparameter, but in their setting where they experiment with context-based QA and Llama 3.1, Quen 2.5, and Mistral 7 billion, they can use the same setting here as the last 50% of the layer.
I see. I understand. Thank you.
Yes, thank you, Asan. So any other questions, please? Okay, so if there's no more questions, I would like to thank you, Ms. Sang, again for presentation.
Thank you, everyone.
Yes, thank you everyone for attending our last seminar in this year. And we do not have the seminar is next week, and the next seminar will be the next 2 weeks. And yes, and thank you everyone, and Happy New Year.
Merry Christmas, Happy New Year.
Thank you, everyone. Merry Christmas and Happy New Year.
Merry Christmas.